Imagine standing on the dusty red soil of Mars, not after a grueling 6-month journey in a cramped spacecraft, but after taking a single momentous step through a shimmering doorway. This idea, which sounds like it was lifted directly from the pages of a science fiction novel, is not just a fantasy. It is a tantalizing possibility rooted in the deepest and most complex theories of modern physics. This incredible concept is known as a wormhole, a theoretical shortcut through the very fabric of space-time itself. It represents a potential bridge connecting two vastly distant points in the universe, or perhaps even two different moments in time. The idea challenges our fundamental understanding of distance and travel, suggesting that the cosmos might have hidden passages woven into its structure. For generations, humanity has gazed at the stars, separated from them by an ocean of vacuum so immense that even light, the fastest thing in the universe, takes years to cross it, centuries to cross it, millennia to cross it. The nearest star system to our own, Alpha Centauri, is over 4 light-years away, a distance so staggering that with our current technology, a journey there would take tens of thousands of years. Wormholes offer a radical solution to this cosmic isolation. Instead of traveling through space, a wormhole would allow us to travel outside of it. The intellectual journey toward the concept of a wormhole began. It began not with a desire for interstellar travel, but with a deep investigation into the nature of reality itself. In 1935, Albert Einstein collaborated with a young physicist named Nathan Rosen. They were grappling with a puzzling aspect of Einstein's equations, the existence of singularities. Singularities, points of infinite density. Gravity concentrated at the heart of black holes. In an attempt to create a mathematical model that avoided these infinities, they published a paper proposing a radical new idea. Their work suggested that what we perceive as a single black hole might actually be the entrance to a tunnel, connecting to another region of space-time. This theoretical structure became known as the Einstein-Rosen bridge. In their model, the bridge connected our universe to a parallel mirror universe, acting as a conduit between two separate space-time sheets. It was the first scientifically grounded description of what we'd later call a wormhole. However, Einstein and Rosen's primary goal was not to invent a method for space travel. To understand how a wormhole is imagined to work, one must first appreciate the modern scientific view of space and time. According to Einstein's theory of general relativity, the 3 dimensions of space and the single dimension of time are interwoven into a single, dynamic, 4-dimensional fabric called space-time. This fabric is not static. It can be bent, stretched, and warped by the presence of matter and energy. A wormhole is a very specific and extreme topological feature within this fabric. It consists of 2 mouths located in potentially different regions of space-time, connected by a throat. The mouths would appear as spherical portals, the throat the tunnel linking them together. The defining characteristic of a traversable wormhole, one that a person or a spacecraft could safely pass through, is that its throat must remain open and stable. As we saw with the original Einstein-Rosen bridge, the natural tendency of such a structure under the influence of normal gravity is to collapse catastrophically. The immense gravitational forces within the throat would pull it inward, pinching it off into a singularity. To counteract this collapse, physicists theorize that a wormhole must be propped open by a bizarre and hypothetical form of matter with highly unusual properties. This substance is often referred to as exotic matter. Exotic matter is defined by its possession of negative energy density or negative pressure. While exotic matter sounds like pure fantasy, there are hints of its existence in the strange world of quantum mechanics. The Casimir effect, for example, is a real, experimentally verified phenomenon, where 2 closely spaced metal plates in a vacuum experience a small attractive force. This force arises because the space between the plates has a slightly lower energy density than the space outside, a form of localized negative energy. However, harnessing these fleeting quantum effects to stabilize a macroscopic wormhole large enough for a person to travel through is an engineering challenge of unimaginable scale, far beyond any technology we can currently conceive of. The quest for a traversable wormhole is therefore inextricably linked to the search for and understanding of this elusive exotic matter. This is the ultimate promise of the wormhole, to shrink the universe and place the stars within our grasp, transforming us from planetary explorers into a truly interstellar species. The concept of a wormhole is not just a fanciful dream. It emerges from the rigorous mathematical framework of Albert Einstein's general theory of relativity. If wormholes are indeed a real feature of our universe, A pressing question arises: where do they come from? Scientists have proposed several theoretical scenarios for their formation, ranging from the cataclysmic birth of the cosmos to the advanced engineering of a hyper-advanced civilization. One compelling idea: wormholes as relics from the universe's first moments. In the instant after the Big Bang, the universe was a seething cauldron of energy. The quantum foam, at the microscopic level, space was chaotic, bubbling and forming tiny fleeting tunnels and bridges. As the universe rapidly expanded and cooled, some primordial tunnels could be stretched to macroscopic sizes, becoming long-lived features of the cosmos. Such natural wormholes would be scattered remnants of the universe's violent birth. They might be incredibly ancient, connecting vastly different epochs of cosmic history and linking distant locations across space. Finding one would be like discovering a fossil from the dawn of time, a direct window into early universe conditions. But even if they formed, they'd need exotic matter to remain stable for billions of years. Another path: wormholes tied to black holes, the universe's most extreme gravity wells. Some models say a rotating black hole might avoid a central singularity. Intense centrifugal forces could carve a pathway to a white hole, the time-reversed opposite of a black hole. Black holes trap everything. White holes, hypothetically, erupt matter and light and cannot be entered. A wormhole could be the throat connecting a black hole entrance to a white hole exit. Yet this model faces massive theoretical challenges. Most physicists think white holes are unstable and short-lived, and traveling such a tunnel would be treacherous. Tidal forces and intense radiation would likely destroy any traveler. Finally, perhaps wormholes aren't natural at all. They might be engineered by ultra-advanced civilizations that can manipulate space-time and produce exotic matter on demand. The wormhole is both a key to the stars and a potential Pandora's box of cosmic dangers. The prospect of harnessing a stable, traversable wormhole opens up a universe of possibilities that could fundamentally reshape the future of humanity. The most obvious and profound application would be for interstellar travel. A journey to Proxima Centauri, our nearest stellar neighbor, would be reduced from a 75,000-year slog to a trip that could be shorter than a transatlantic flight. This would effectively open up the entire galaxy for exploration, colonization, scientific study. We could visit planets orbiting distant stars, search for extraterrestrial life firsthand, and witness cosmic phenomena that are currently visible only through the faint light captured by our telescopes. Furthermore, according to the theory of relativity, any wormhole that allows for faster-than-light travel between 2 points in space could also, in principle, be manipulated to allow for travel into the past. This raises the specter of time travel paradoxes, such as the famous grandfather paradox, where a traveler goes back in time and prevents their own grandfather from meeting their grandmother, thus preventing their own birth. The ability to alter the past would unravel the very fabric of cause and effect, which is the foundation of our understanding of the universe and our place within it. Some physicists, like Stephen Hawking with his chronology protection conjecture, have proposed that the laws of physics may conspire to prevent time travel on a macroscopic scale, perhaps by causing any attempt to create a time machine to self-destruct in a feedback loop of energy. For now, these questions remain in the realm of theoretical physics, but they highlight the profound responsibility that would come with mastering such a powerful technology. The wormhole is both a key to the stars and a potential Pandora's box of cosmic dangers. While wormholes remain a purely theoretical concept, that has not stopped astronomers and physicists from devising ingenious ways to search for them. Since a wormhole's mouth would not necessarily emit light on its own, we cannot simply point a telescope at the sky and expect to see one. Instead, searches look for subtle effects on their surroundings, particularly on the light from distant stars. One of the most promising methods involves looking for specific patterns of gravitational lensing. Just as a massive galaxy can bend the light from objects behind it, a wormhole mouth would warp spacetime and act as a lens. Its lensing would be distinct from a black hole, distinct from a star. Normal massive objects typically brighten background stars as they pass in front, but some models predict a more complex wormhole pattern, a rapid double-peaking brightness profile. Astronomers are scanning huge sky survey datasets searching for anomalous lensing events. So far, no definitive candidate has been found, but the search continues as instruments improve, leaving a faint hope of finding a cosmic shortcut. Another approach studies gravitational waves, Ripples in space-time from cataclysmic events. The Laser Interferometer. Gravitational Wave Observatory. Other detectors have observed waves from collisions of black holes and collisions of neutron stars. Physicists can predict the precise waveform, or chirp. If a wormhole took part in a collision with another wormhole with a black hole, the gravitational wave signal would be unique. The merger's final moments and the ring-down as spacetime settles would show different frequencies and decay. Echoes of exotic structure. The concept of the wormhole stands as one of the most daring and imaginative ideas to emerge from modern physics. Born from the elegant equations of Einstein's relativity, it has grown from a mathematical curiosity into a serious subject of theoretical inquiry and a powerful symbol of humanity's deepest exploratory urges. It represents a potential solution to the tyranny of cosmic distance, offering a vision of a future where the stars are not just distant points of light, but accessible destinations. While we are currently a very long way from building such a cosmic subway system, or even navigating one, the study of wormholes continues to provide invaluable insights into the fundamental nature of gravity, space-time, the quantum world. The path forward in wormhole science is twofold. On one hand, theoretical physicists must continue to refine their models, searching for solutions to Einstein's equations that describe stable, traversable wormholes, without requiring impossible amounts of exotic matter. This work forces us to confront deep questions about negative energy, quantum gravity. Every new paper, whether it proves or disproves a model, adds a crucial piece to the puzzle, helping us map what is physically possible versus what remains science fiction. On the other hand, observational astronomers will continue their patient search for astrophysical signatures of these elusive objects. With each new generation of telescopes, gravitational wave detectors, and sky surveys, our ability to scan the cosmos for anomalous phenomena grows more powerful. The discovery of a single unambiguous wormhole candidate would be one of the most significant scientific breakthroughs in human history. It would confirm the universe is stranger and more wonderful than we imagined, and galvanize a global effort to study, understand, and perhaps one day reach this cosmic gateway. Ultimately, the enduring appeal of the wormhole lies in what it represents: an open door in our understanding of the universe. It reminds us that our current knowledge is incomplete, and that vast, undiscovered territories may still lie hidden within the laws of physics. Whether we ever find a real wormhole or not, the quest inspires us to keep asking audacious questions, to challenge our assumptions, and to continue our relentless exploration of the cosmos. The idea of a shortcut through space is a testament to human curiosity,